Welcome back! Today, we're diving into something that's, well, at the very heart of AI. I mean, think about it. Your GPS, a character in a video game. How does a computer program figure out the best way to get from point A to point B? It's this grand quest, really, and today we're going to unpack exactly how they pull it off.
Okay, so here's how we're going to tackle this. First, we'll look at the quest itself. What is a search tree? Then, the labyrinth, or how these searches can get totally lost. After that, we'll check out the toolkit, the secret weapons algorithms use. We'll hit the crossroads to choose a strategy. And finally, we'll pull out the scorecard to see how we measure success. Let's jump in.
All right, first up, the quest. So, how does a program, say one trying to get you from Amarad to Bucharest in Romania, even start to think about finding the best route? Well, it definitely doesn't just guess. What it does is it starts building a map of every single possibility. It's a structure that lets it actually reason about all the different paths it could take. So this map, we call it a search tree, and it's a really good name for it. Just picture a real tree. Your starting point, what we call the initial state, is the root of that tree. From there, the algorithm expands that location or node by looking at every possible move it can make. Each of those moves creates a new branch leading to a new spot, and we call those child nodes. And just like that, you've got the first branches of your search tree.
And here's a perfect example of how that works. We're starting at Arad. The program looks at the map and says, okay, from here, I can drive to Zerend, Sibiu, or Timisoara. Boom! 3 child nodes are generated. Each of those cities is now a new frontier, a new place to explore from. And the algorithm just keeps doing this, over and over, expanding node after node and growing this absolutely massive tree of potential paths, all trying to find a way to our goal, Bucharest.
Okay, section 2, the labyrinth. Because see this simple process we just talked about? It has a massive critical flaw. If the algorithm isn't a little bit smarter, it can literally get trapped and just wander around in circles forever. Let's take a look at exactly how this nightmare scenario happens. So, imagine a really simple map. You start at S and drive to city A. Great. From city A, you can drive to city B. Easy enough. But what if the road from city B leads right back to city A? Well, our naive little program, just doing its thing, goes from A to B. Then it expands B and sees, hey, I can go to A. So it turns around and goes back. Then it gets to A and says, oh look, I can go to B. And back it goes. You see the problem? It's completely trapped in an endless loop, generating an infinite search tree and failing its mission big time.
And this quote just hits the nail on the head. Algorithms that forget their history are doomed to repeat it. The core problem is a lack of memory. These little back-and-forth trips are called cycles, and they're really just one example of a much bigger problem called redundant paths. And that's just anytime you have more than one way to get to the same exact spot. An algorithm with no memory is just going to blindly explore every single one of those paths, wasting a ridiculous amount of time and energy.
Okay, so how do we fix this? How do we get our algorithm out of this labyrinth of infinite loops? Well, it needs an upgrade. It needs a proper toolkit. Think of it like a detective's kit. It needs a memory to keep track of where it's already been, a notepad to take notes on its journey, and a to-do list so it can stay organized. The first, and honestly the most important tool in this kit is called the explored set. And it's exactly what it sounds like. It's the algorithm's memory. It's just a simple list of every single place it has already visited and explored. So before it even thinks about adding a new path, it just quickly checks the list. Is this place on the list? If yes, it just throws that path away, no more repeating itself. Simple, but so powerful.
And you have to understand, this one tiny addition is an absolute game changer. It takes that basic flawed tree search we started with and transforms it into a much smarter graph search. This simple memory is literally the key. It's the thing that guarantees our algorithm will never ever get stuck in an infinite loop again.
All right, next tool, the notepad, or the algorithm's diary. See, for every place it considers, it doesn't just jot down the city's name. No, it creates this really detailed data structure called a node. It's like a full diary entry. First, you have the state. Where am I right now? You know, like Arad. Second, the parent. How did I get here? So it can always trace its path back. Third, the action. What exact move did I make? And finally, and this one is super important, the path cost. How much has this trip cost me so far? It keeps a running total of the distance or time from the very beginning.
And last but not least in our toolkit, the to-do list. The algorithm needs to stay organized, right? It's generating all these potential new places to go, these child nodes, but it hasn't visited them yet. So how does it keep track of everything? It uses another data structure called the frontier. You can think of this as its literal to-do list. It's a queue that just holds all the nodes that are sitting there waiting to be explored.
Now, this is where things get really interesting, because how you organize that to-do list, it completely changes the entire search strategy. For example, you could use a priority queue, which always pulls out the node with the cheapest path cost first. Or you could use a FIFO queue, that's first in, first out, which is just like a line at the store. It takes the oldest node first. And then there's a LIFO queue, last in, first out, which works like a stack of plates. It always grabs the newest node right off the top. This one decision, how you order the list, defines the whole personality of your search algorithm.
All right, let's hit pause and recap. Our algorithm is now fully kitted out. It's got its memory, the explored set. It has its diary, the node structure, and it has its to-do list, the frontier. It's ready to go. But it still has to make a choice. It has to decide which of those nodes on its to-do list it's going to explore next. And this choice, well, this choice is everything.
And these strategies really fall into two big categories. On one side, you've got what's called uninformed search. You can just think of it as blind search. The algorithm has absolutely no clue where the goal is. It's like you're in a pitch-black maze, and your only strategy is to keep one hand on the wall and just keep walking. Now, on the other side, you've got informed search. This is where the algorithm has a hint, an estimate, we call it a heuristic, of how far away the goal is. It's like being in that same maze, but now you have a compass that's always pointing you towards the exit. Obviously, that's going to help you make much smarter choices.
So, okay, we've got these different strategies, but how do we know which one is actually better? We can't just guess. Turns out, computer scientists have a standard scorecard they use with 4 really important criteria for judging any search algorithm.
And this scorecard is great because it gives us a common language to compare any algorithm. We just ask 4 key questions. Number 1, completeness. Is it guaranteed to find a solution at all, assuming one exists? Number 2, optimality. Will it find the best solution, like the absolute cheapest or shortest path? And then we look at efficiency, time complexity. How long is this thing going to take to run? And finally, space complexity. How much memory is it going to eat up during the search? These 4 are the gold standard. Now, when we're talking about time and memory, the difficulty of any given problem often comes down to this one little variable, B, which stands for the branching factor. All that means is the average number of choices you have at every single step. And why is this so critical? Well, because even a pretty small branching factor, say you have 10 choices at every step, can cause the total number of paths to explore to just explode. We're talking exponentially. The time it takes and the memory it needs can get out of control fast.
Which brings us to our final thought for today. We've laid out all the groundwork, right? We've built our intelligent problem solver, we've given it a memory and a plan, we've even set up the scorecard to judge how well it does. But the real burning question is, when you actually put these strategies head to head, when you take something like a breadth-first search and pit it against a depth-first search, which one actually comes out on top? Well, that's a story for our next explainer.